Okay, so hello, my name is Liam. I'm a student at the University of Liverpool. I'm going to present my piece of work for MIUA, which is based on a new variational segmentation model and how we can implement it into a neural network framework. So to begin with, I'm just going to do a brief overview of variational image segmentation and the methods behind the approaches that we can take. So apologies if you're familiar with this. It's just to set the scene, sort of. So in general, we want to find some contour gamma, which partitions objects in an image. And typically in the variational approach, there are two different approaches that we can take. The first is global segmentation, which is displayed on the top row here, which is the task of finding every object in an image. Or another approach, which is less studied, is selective segmentation. So given some clicks, usually defined by a user, to indicate which object we're interested in, only find the contour around those objects specifically. So in this example in the bottom row, we clicked on the triangle and the circle, and the contour gamma has found the triangle and the circle. So variational models typically involve minimizing over a certain functional. And functionals typically consist of three things for selective segmentation. First is the regularizer, which introduces some kind of prior knowledge and also ensures the problem is well posed. Typically, we use just total variation for this. The second part is the intensity constraint. This just ensures that the region inside our contour is roughly homogeneous. Of course, there are intensity constraints that deal with intensity and homogeneity, but for our purposes, we're going to look at homogeneous objects just to make things a bit more simple. And for selective segmentation, usually you use some kind of distance constraint to penalize the solution from evolving too far from the user clicks that we just discussed. So throughout this, we're going to denote the user clicks as this capital fancy M, or I might refer to it as the marker set. Okay, so one recent segmentation model is the Roberts-Chen model. So this uses an edge-weighted geodesic distance constraint to achieve selectiveness. So this is composed of the regularizer, is the first term. This term penalizes the length of the contour, and it has an edge detector in there as well. The next two terms are Cham versus fidelity terms. You might be familiar with this. So the basic principle behind this is that C1 is the average intensity of the region inside our contour, and C2 is the average intensity of the region outside our contour. And this final term is the edge-weighted geodesic distance. This aims to put a penalty on regions outside the object that we're interested in. And I'll discuss this now. So ideally, in a distance constraint, we want the object that we're interested in to have a constraint of 0, and objects outside to be larger than 0. So if you're using Euclidean distance, you can see that the constraint on the triangle is rather varied. It roughly ranges between 0, 0.4. It's not a great distance constraint because it's heavily dependent on user input. In contrast, the geodesic distance is really robust. You could put the user input anywhere on the triangle and you get this output. And it's much more intuitive because it only increases when an edge is detected. So we find the geodesic distance by solving this iconal equation, and these edges are doing all the work. So if an edge is detected, the distance goes up. So to get from here to here, you have to travel over this edge. So the constraint is 0.5-ish. To get from here to here, you have to travel over two edges. So the constraint is large. So using this as a constraint makes your segmentation really robust to both user input and parameter selection. However, this is only the case if an edge is able to be detected by the gradient. Sometimes, particularly in objects where there are low contrast at the boundary, for example, in this image, if we're interested in this, an aneurysm of the abdominal aorta, it's got quite large, this quite distinct circle here. However, this object here is not part of the abdominal aorta, it's just a nearby object. It has essentially the same intensity as the abdominal aorta, and it is touching in a few pixels here. And because of those pixels that are touching, the gradient is unable to detect an edge. And you can see with this user input, this is the output of the geodesic distance, and the constraint on this region, which we don't want, is essentially 0. Ideally, we'd want it to be larger than 0, so we can put a constraint on this region. But if we did segmentation with this, you'd essentially get the abdominal aorta and a little circle here, which we don't want. So in order to combat this, our proposed model uses area constraints to both, so it makes use of the geodesic distance to put constraint on objects away from the marker set. But if the geodesic distance fails, particularly in regions of low contrast, we also introduce this area constraint here. So what this is doing is ensuring that the area inside our contour, so this one, is as close to possible as A1. Oh, I forgot to add it on the slides, but A1 is the area of the polygon formed by the user clicks. So in this example, the area would just be the area of this rough circle. And ideally, we'd want the area of our final segmentation result to be as close as possible to the area of A1. This model is fully convex. An explicit proof is provided in the conference paper you can find, and you can solve this using any optimization method you prefer. We found the Euler-Lagrange equations and just use additive operator splitting to solve it. Okay, so as well as the variational framework, we compose this into a deep learning framework. So it just does some notation. N total images, and we're just using the notation where U, W, Z, M is the output of our network, where we have a network with weights W, and the inputs to the network is the image Z, and this boldface M, which we're going to define this as the polygon formed by the user clicks. So just shorthand, UJ means that the JF output with the JF inputs. So we can put this into 3 frameworks, both so supervised, semi-supervised, and unsupervised. So first of all, the supervised algorithm, we make the loss function to be this. So this is very similar to the variational approach. The only difference in this is that the this fidelity term. So in the variational approach, this fidelity had the image minus C1 and the image minus C2, where C1 was the average intensity inside the contour, C2 is the average intensity outside the contour. In the supervised approach, we can make use of ground truth labels. So for the supervised approach, we call this V, where V is the ground truth label, and C1S, C2S are 1 and 0 respectively. as you'd expect from the binary mask from the ground truth label. And in addition, you have the geodesic distance, the area constraint, and the regularizer. So these A1 and DG are calculated using the polygon formed by the marker set. And this is calculated before training and just plugged into the network to speed things up. So the unsupervised approach is much more similar to the variational approach. We have the regularizer, edge, area constraint, and geodesic distance. And in this case, we make use of the image in the fidelity. So the image minus C1 unsupervised, image minus C2 unsupervised. And in this case, this is a typo. In this case, we have C1 or C2 to be fixed to be the average intensity inside and outside the polygon formed by the user input. And this is calculated like this. So the user clicks on points, we fix C1, C2, we calculate A1 and the geodesic distance from these user points, and then we train suitably. In addition to those two approaches, we can take a semi-supervised approach where we combine the two. So if we have N1 ground truth labels available, we use the supervised approach. And for the rest of the images, we use the unsupervised fidelity. Okay, so this is the architecture. We make use of a unit-like network where convolutions are applied downwards and upwards. And since we have two different inputs, image and the binary mask, those are treated separately on the way down. They're joined with a dot product, and then we go upwards to output a segmentation mask of the same size as the input. Okay, so just some results to finish off. This is just purely variational at the moment. We'll talk about deep learning in a second. But you can see we're going to compare with the Chen model, which is our model that isn't using area constraints. And this is ours, which does use area constraints. So given this input here, these are two images of the abdominal aorta with an aneurysm. And you can see there are two objects, and there's an object in both of them that isn't a part of the aneurysm, as shown by the ground truth, but is the same intensity and is touching. With our area constraints, we're able to stop the leak in the old model and make it much more similar to the ground truth. Okay, and so for the deep learning results, we're making use of these LITS data set, which is liver tumors, has the details of what we did. You can pause if you like. So this is the dice scores of the whole test set for the 3 of our approaches and 2 standard approaches. So we have the unsupervised, semi-supervised, and supervised. In general, the supervised is the best. And so these 2 approaches are standard units, where the first one is with the dice loss function as the loss, and the second one uses binary cross entropy as a loss. So that these are both supervised approaches. And just you could see some deep learning results. So we display the classical formulation. So in the variational formulation, and these are the results from the unsupervised, semi-supervised, unsupervised, and this is the ground truth. And we have another set of slides. So in general, the supervised does outperform. The advantages of the classical formulation is that you do have room to tune the parameters if you wish. So yeah, thank you for watching my presentation on a new convex variational model and its deep learning framework.